Now to go to dynamics, from our system, from the calculation, and then from the introduction as well. Here I want us to study some things about introduction. Okay, the reason for dynamic simulation is to check the deviation of our steady state, the deviation of our plans from steady state simulation. Now, for instance, we are able to get a T acetate to be 115.2. In reality, this may not really form, because this steady state means assumption of there is no deviation in anything, probably the environmental factor, the equipment, and every other thing. So that is what dynamic simulation is really portraying. That is what it's showing. We want to study that in real life, probably because of the size of the equipment that we are going to be using, we may not be able to achieve this in reality. So we want to check that are we going to be able to achieve it. Then if we are not going to be able to achieve it, then we want to make use of what we call controller to control some variable or parameters in order for us to achieve this and many other things that have been calculated in the steady state form. Okay, now before you do any steady state simulation, you must know the size of all the unit operation involved, all the size of your equipment, the physical dimension, as we have seen as it is here. You see, to convert steady state simulation, several items have to be taken care of. For instance, this size of all equipment must be specified and the control structure must be devised. Okay, so that control structure, we are going to be the one to pick it, trial and error, or some other things. Okay, now this equipment, now we want to enter the size of the equipment for the aspen plus reactor. Okay, and before I proceed, I would like to mention that there are two types of dynamic simulation in aspen plus, and even in any other simulation. There is flow driven and there is pressure driven. Flow driven is the simplest, where there is no need of you use the flow to control the system, while pressure driven, you use the pressure equipment like valve, like compressor, like pump to do the control, and that is the rigorous and is the most detailed and safe type of control or dynamic study. Okay, because there can be increase in flow and the pressure, or there can be the flow can continue and the pressure is low, and even the flow may be controlled while there is high pressure buildup inside your system, and that will not be too good when there is high pressure buildup and the flow continues. Okay, now when you take some other study on the dynamic and control, probably you read some things up, difference between flow driven and pressure driven, you get to know, and we'll get to pressure driven simulation as well. For now, we are going to be using flow driven process. Okay, and we are going to be inputting the dynamics of the unit operation. Okay, now to do that, we go to our blocks and we name this reactor B1, and we are going to be making use of B1, and under B1 there is something we call dynamics. Okay, that is when you are going to enter the physical dimension of the unit operation you are trying to control. Then we click on it, dynamics, and can you see it's not bringing anything? Why? Because we are not in dynamics already. So to go to dynamics, we go to our ribbon tabs, and under dynamics we pick dynamics, then we click on dynamics mode. We go to dynamics mode before you can input the physical dimension of your system. Okay, we click on dynamics mode, and here we have it. And from our problem statement, we're able to see that our system is having a vessel type of vertical and the head is flat. Okay, so we can make use of that. Instead of elliptical head like this, the geometric is flat, and the length were given and the diameter were given to be 0.45711 meters. Okay, 0.45711 meters, 0.45711 meters. Then by that we are good to go. Can you see all of these were not highlighted before? Okay, why? Just because we've not input the required parameters to perform dynamic simulation. And the required parameters is that you know the size of your equipment, you know the geometric of your vessel of your equipment. Okay, now to export our simulation to dynamics, now you either make use of this ribbon. If it is flow driven, you want to make use of flow driven. Okay, so you can make use of it. If you want to know more about flow driven, you can go to the app and try and search on flow driven. And if you want to use pressure driven, but now we are going to be using flow driven. Okay, pressure driven is a rigorous and very detailed simulation. Now we go to either use this or you make use of exports. Under files, you export, then you click on flow driven. Of course, if you've not input the dynamics of the system, then your flow driven will also not work under export as well, mind you. So you can make use of this. When you click on export, then it's going to bring it. Then you have to save it with a new name, or you make use of this name already. But under here, it has been saved. The saved type is now flow driven dynamic simulation instead of our APWS, that's aspen plus steady state before. So you make use of this, we save it as this. Okay, then now it brings warning. It's going to change something. For instance, now is the warning here is that reaction program name as it has been named. That's why I wanted to change it to that. It's not a valid aspen plus notation or keyword. Then it has changed the name to this. So we are going to go. I can close this. Now my steady state simulation has been exported to dynamics. Okay, now to open what has been exported to dynamics, now there is another package that we call aspen plus dynamics. Okay, you bring this one down, then we go to our ribbon, then click on we type and search for dynamics. Can you see this aspen plus dynamics? And that is where we can control it. So I click on this to open aspen plus dynamics. Okay, now we are now in aspen plus dynamics page. Now to open our exported flow sheet, we go to files, then we click on open. Alright, we are going to open. You see, this is the name that I used to open it when I exported it to dynamics. Then if you export it very well, you are going to see this, the name you open it with. Then you click on the name and you open. Okay, by default you can see that some control scheme or control structure has been already inserted on our system. Now that is how Aspen Plus works. Aspen Plus have a default control strategy that will have been input into your system. Okay, just like they will have temperature, pressure, and level controller. Those are the default controller that will be inserted where necessary. Okay, and this is the default one for our reactor. We have temperature controller, and we have we have level controller as well. So these are the default controller that we are using in Aspen Plus. Alright, then Aspen Plus will have given some control tuning parameters to our system, just as it has given us this. You can change this anyway, don't worry. When we are going to take another tutorial where we can change every of those parameters. Now in order for us to view or change the parameter, we can double click on the controller. For the temperature controller, we can double click on it, and it's going to bring us the the page where we can control it. Okay, this is the set point. Okay, this is the process variable, and this is the operator output. Now, another thing I want you to know is that the set point is going to be your target. Okay, and the process variable is going to be what you really want to control. Okay, and what do you want to control? We are going to be using something to control it, and that is the output or manipulated variable. It is well explained in the introduction, so if you really didn't understand, you can go back to the introduction page and see. Now we are going to go to no, we are not using plot, we are going to be using configure. I want to show us something. Now under the configure page, we can see the set point. Now this set point is going to come the set point came from our steady state simulation. Is it steady state parameters that are being inputted, the steady state value rather. Okay, and if you see that the temperature of the system when we input it while we're working with the reactor is operating at 70 degrees C, so that is our steady state value. Okay, at 70 degrees C, and at 70 degrees C, okay, in order for us to maintain 70 degrees C, the steady state simulation was able to calculate it that there is need for us to be removing the heat of this amount at every interval, and that's the reason why we have initial output. And that initial output means when the difference between the set points and the process variable which is being controlled, when the difference between them is 0, and that is what we call bias, as you have been taking in your lecture, because there's bias signals. So this is the bias signal that shows that if there is no change, if there is no deviation, there is no difference between the set point and the process variable, then you should maintain the flow of probably the cooling water should be carrying this energy, you should be removing this energy. Okay, and this is the gain, the steady state gain, and we have the integral time as well, and you know the derivative time as well, as it has been explained in the introductory part of the video. Alright, now I like us to look at the range, and the range, this default range is from 20 degree minimum and 120 degree maximum, and the outputs as well, the output variable, that is the amount of cooling energy, the amount of energy to be removed by the cooling water should be from -17 degree and 27 degree, minus 17.27 kilocalories per hour. Okay, now it's because I'm using the unit I'm using has been integrated to dynamics. The units I used in this steady states has been used in the dynamics as well. Okay, then another thing I'd like you to know is that these values go very wide from our set point and the process variable. Then we can change it, but I think the problem statement asks us to make use of. Now we have to simulate the reactor model. That's what we have done in the steady state. Now we should report the controller tuning parameters and the control action used and constraints, that is the boundary limit imposed. Okay, we have to record the default tuning parameters. This may not work, or this may not be okay for your system anyway. It can be changed, as I have said. Now the default tuning parameter, the gain, the integral time and the derivative time for the temperature controller has been given. Okay, and we are told to look for the boundary, which is the limit, that is the minimum and the maximum for each variable. The process variable and the set point are given as this, and for the outputs, the process variable, for the manipulated outputs. Okay, now let me close this, and I can close this as well. Now to the level controller, you can double click on it and we'll go to configure, and under the configure you can see that the set point is around very close to 1 meter of the level. Okay, and in order for us to maintain this level, the flow of the outlet of the product must be around this kilogram per hour. Okay, and these are the initial, this is the default tuning parameter that was given. Okay, and this is the range, the limit. Okay, is either the process variable, that is the level of the reactor, is either it should be 0 or as the minimum, and 1.8 very close to 2 as a maximum. Okay, this may not be allowed because you cannot allow the fluid inside the reactor to be empty, but this is the default. We just want to record the default. Now there's something we call the controller action. Should it be direct or reverse? Now Aspen Plus can really choose which one it should be. Now for our level controller, we are able to see that the default one is direct, which is okay. Now direct means that when the process variable, okay, increases, when the set point increases, okay, then you increase the level of the manipulated variable. In other words, it means your set point, you have the level, from the calculation of the steady state, we're able to say that the level of this steady state reactor, the level should be 1, that is the liquid level should not be more than 1. Okay, as the system is operating, there is tendency of the that the level should go more than 1. If it goes more than 1, then that shows it has increased. Okay, it has increased. Then that shows that the manipulated variable, which is the liquid, which is the outlet flow, should also increase. That is what we call direct. Okay, from this statement, we can see that the direct acting controller system increase the output signal as the input signal to the controller increases. Okay, that is, the input signal to the controller will be the signal of the process variable. What does the controller receive from the reactor? Now the input signal structure, if it increase, the output signal from the controller must okay, this one is for the case of the reverse controller, reverse action rather. Now I like us, we can change the control parameters as the problem has really given to us. We are to report it. Then we want to investigate the servo and the set point, that is the set point performance of the default liquid level and the temperature control algorithm. I want to score the effects. Okay, now for the set point tracking, okay, we want to investigate this default. Are we able to achieve with these default parameters, be able to achieve the control of our system? Okay, in order to view that, we double click on the level. For the level, we have this. Then we can make use of, okay, now we can make use of plots and put it like this. Then for the temperature, now let's study the level first. Now I can, in order to run it, to run the program, and let's see how it's going to work, the performance of this tuning parameter, of this tuning parameters, we want to check. To do that, we go to run here, then we click on run. Oh, sorry, I'm supposed to run it for some time. Let me stop that. Oh, alright. In order to choose our runtime, we press Ctrl F5. So we want to run this system for 5 hours. first 5 hours and I click OK. Then I want to run, and I can run it as this, and let's see the behavior of the system. Okay, can you see this is the process variable, which is in blue, and the set point. There is no deviation between the set point and the process variable. Alright, so there is no any differences between them. Then if you want to check, you can check for the temperature as well by double clicking on it, and let's see the plot. The plot for the temperature also does not really show any deviation as they run. Okay, this is the process variable and this is the set point. That means there is no deviation in the set point and the process variable. That means the system actually have a very good behavior. Okay, so I think I'll have to pause this video at this time, then we are going to continue in the next video. Thank you.